Let's talk about tests for independence. In a hypothesis test of independence, we want to test to see if a variable x is independent of a variable y. Often we call x the independent variable and y the dependent variable. Instead of using the word variable, we can think about this x value as a factor of a population. And we're comparing it to another factor. So x is one factor, and we want to know if this factor is independent of the y factor. Oftentimes, the independent variable will be considered our row variable, and the dependent variable y will be considered our column variable. To do that, we look at a contingency table, which we saw when we talked about probabilities. So here's an example of a contingency table. It compares two variables. The row variable here is whether or not the person contracted the flu, and the column variable is whether or not a person got the flu shot. Using a contingency table like this, we might be able to test the claim that getting a flu shot, or getting the flu, is independent or dependent of whether or not the person got a flu shot. So to fill out this table, we would need to take a random sample of volunteers. So let's say we take 1,349 random volunteers, and we ask them whether or not they contracted the flu this season and whether or not they got the flu shot this season. So suppose of those 1,349 volunteers, we find 469 of them to have not contracted the flu, but they did not get the flu shot. And 410 of them did also not get the flu, but they did get the flu shot. 279 of these volunteers contracted the flu and they did not get the flu shot. And for our last cell, we find that 191 of them contracted the flu, and even though they got the flu shot. So again, our row variable here is whether or not the patient got the flu, and our column variable is whether or not the patient got the flu, whether or not they got the flu shot. We call our sample size here the grand total, and in order to find the grand total, we add up all of the cells in the table. So each of those four numbers added up together came from our sample size of 1,349. So let's talk about the components that go into a test of independence. First of all, starting off with our hypotheses, since this is a hypothesis test. We'll have the null and the alternative hypothesis, just like we always do. The null hypothesis states that the rows and the columns, so the variable that we're comparing in the row and the columns, are independent from one another. And this is always going to be the case in any test for independence. The null hypothesis claims independence, and the alternative hypothesis states that the rows and columns are not independent. So in other words, the rows and the columns are dependent. Now, in order to do a hypothesis test for independence, we need to look at our observed values. So those are what we collect in our contingency table from our random sample, and we need to compare them to our expected values. So we have observed and we have expected frequencies. Again, our observed values come from our sample data, while the expected frequencies are often calculated. The way that we calculate our expected frequencies is actually to use probability techniques that we already discussed previously in this class. And they're calculated based on any random sample of size n that we have from our observed, right? So if we have n observed values, we would calculate the expected frequencies based on our n, that same size n. And the way that we calculate our expected frequencies is to use the formula where we take our row total and we multiply by the column total in our contingency table, and then we divide by that grand total number. So now what do we do with the observed frequencies and the expected frequencies? We calculate our test statistic. And just like with the goodness of fit test, our test statistic is a chi-square test statistic. And the formula for calculating this test statistic is exactly like our goodness of fit test. You take the difference of each corresponding observed and expected value, you square that, you divide by the expected value, and you add them all together depending on how many cells you have in the table. So with our flu example from earlier, we had 4 cells, so we would have had 4 fractions to add up in our sum, 4 different O's and 4 different E's to take the difference of. Now the degrees of freedom for the chi-square distribution for a test of independence is a little different than for the goodness of fit test. The degrees of freedom is going to be the number of rows you have minus 1 times the number of columns you have minus 1. So once you've calculated your test statistic, you want to plot your test statistic on a chi-square distribution and calculate your p-value. So again, we'll have a right-tailed test for our test of independence. And so that shaded in area is my p-value. And the conclusion that we make, again, it's the same as it's been all semester. If your p-value is less than your significance level alpha, you're going to reject the null hypothesis. And if your p-value is greater than your significance level alpha, you are going to fail to reject the null hypothesis. Because the null and the alternative hypothesis never change in a test for independence, remember the null hypothesis supports independence while the alternative hypothesis supports dependence. That means that the interpretation of our conclusion is also straightforward. If you're going to reject the null hypothesis, what that means is that you cannot support independence. But by failing to reject the null hypothesis, it means that independence is possible. So a vote to fail to reject the null hypothesis means that you can support independence. Let's go ahead and determine whether getting the flu is independent of whether or not you got the flu shot. We'll use a 0.05 significance level to test this claim. So the first thing that I like to do with a test for independence in a contingency table is I actually like to draw an extra row and an extra column so that I can go ahead and write down row totals and column totals. So if I add 191 to 410, I get 601. If I add 279 to 469, I get 748. And if I add these two numbers together, 748 and 601, I get my grand total, which is 1,449. And then for my row totals here, 191 and 279 gives me 470, and 410 and 469 gives me 879. And again, if I add 470 to 879, I again get this grand total. And we need that number in order to calculate our test statistic. So now let's go ahead and write down what our hypotheses are. So remember, our null hypothesis is independence, and our alternative hypothesis is dependence. But instead of just writing those words, let's go ahead and write a sentence in the context of the problem. So what does it mean to be independent in the null hypothesis? It means that getting the flu is independent of whether or not the person got the flu shot. And our alternative hypothesis will state that getting the flu is dependent of receiving the flu shot. So again, independence is always the null hypothesis, and dependence is always the alternative hypothesis. Now let's calculate our expected frequencies. For each cell in the table, we'll have an expected frequency. So we'll have one for, this is our first cell, our second cell, third cell, fourth cell, etc. And the way that we calculate our expected frequency is to take our row total, multiply by our column total, and divide by the grand total. So for cell 1, our row total is 470. We're multiplying by 601 and dividing by 1349, our grand total. And so the expected number for cell 1 is 209.4. For cell 2, we'll have 470 times 748 divided by 1349, which gives us 260.6. And we'll continue this process for both cells 3 and cell 4. These expected values or expected frequencies represent the amount we could be getting in any random sample of size 1,349 for each of these boxes. So we said 209 people is the number we would expect to have contracted the flu even though they got the flu shot. We would expect 487.4 people to have not contracted the flu and they did not get the flu shot. So these are our expected values. Now we're going to calculate our test statistic by comparing each of these expected values, expected frequencies, to the observed frequencies. So let's find our test statistic. Our chi-square test statistic is the sum of the differences of the O's and E's squared divided by its expected frequency. So we add all of those differences squared together. So for the first cell, we have 191 for the observed minus 209.4 for the expected. We'll square that difference and then divide by 209.4. For the second cell, our observed was 279. Our expected is 260.6. We'll square that difference and then divide by the expected, which is 260.6. We'll continue this process for the next two cells so that we have these four expressions to evaluate and then add together. So there we have 1.6168 for the first for this first fraction here, and then this one goes with this one here, here. Anyway, when we add them all up, we get 4.4752. Let's go ahead and plot this test statistic on the chi-square distribution. Remember, the degrees of freedom for a test of independence is to take the number of rows minus 1 and multiply by the number of columns minus 1. So we have 2 rows and 2 columns in this example, which becomes 1 times 1. So the degrees of freedom is 1. So we have one of those sort of exponential version looking curves here for the chi-square statistic. And we plot it, and our p-value is the area to the right of 4.48. Using the help of technology, we calculate the p-value to be 0.0344. So now we come to our conclusion. Our hypothesis test was done at the 0.05 significance level, and our p-value of 0.0344 is less than our significance level alpha. So therefore, we reject the null hypothesis. By rejecting the null hypothesis, we're rejecting independence. So there is insufficient evidence to support the claim that getting the flu is independent of having received the flu shot. So we are rejecting that getting the flu and getting the flu shot are independent of one another. So it seems that they are dependent on one another, which means that the flu shot appears to be effective. So we did that entire example pretty much by hand, calculating the test statistic and each of the expected values. But I do want to show you that Statistic will shorten this procedure for you significantly. So I took my 4 cell values here from my contingency table, and I put them into Statistic exactly how I saw them in the problem, right? This was cell 1, and then we have the 279 were the number of people who got the flu but didn't get the flu shot, etc. So they're all in the same place there. And then I'm going to go to analysis, and I'm going to contingency tables. I select my significance level, and I check which columns I want to include in my analysis. So I have data here in columns 1 and column 2. If you have a larger contingency table, you'll check more of these boxes. And then I push evaluate. And again, you can see my degrees of freedom, my test statistic, and of course my p-value, which helps me make my conclusion. So hopefully that lightens your load a little bit. Make sure you're using StatDisk.